Yes, this is the lesson material for today. And today, the morning session, it will be me cover the motivation and also writing the performant Julia code, these two episodes. In the afternoon, Pedro from HPC2M in Umeo University, we talk about multithreading and distributed computing, these two episodes. Yes, let's come to this motivation. We talk about the Julia, and today we are going to talk something new about the high performance computing. So, what is high performance computing, or we can call it HPC, and why Julia is suitable for high performance computing for this scientific computing or scientific research? Yeah, at the beginning we talk what is HPC. HPC means that use large computer resources to solve computationally demanding or data-intensive problems. It need to handle lots of data. You need to handle lots of computations. And for example, the prediction of weather and the climate event. We all know that the weather and the climate can change. The changes can significantly impact the human safety, health, and ecosystem and the economy. Therefore, a reliable forecast prediction could help to manage the effect of short-term weather event and also the long-term climate changes. I can see that nowadays the weather climate centers, not only in Sweden or the SMHI in Norrköping, but also in other countries, rely on the power of HPC resources. And actually, for HPC resources, they are always named as HPC clusters. They are equipped with the CPUs before, but now most of these resources are equipped with GPU card. Here is the list of these top 500 HPC clusters in the world. This list was released last month for the scientific computing conference in US. Uh, I can see here is I just mentioned some. Here is the top 10 HPC clusters on the world to see with their specific equipment. Number one, EA Captain. It has AMD MI300A. Number one is EA Captain Cap 10. It is located at LNL, which is Lawrence Livermore National Lab in California, and equipped with AMD MI300A GPU. Number two, Frontier is located at Oak Ridge National Lab in Chicago area. Equipped is AMD MI250X, same GPU. Number three, Aurora, it is at Argonne National Lab. It's the Tennessee area. So it is equipped with Intel GPU. Yes, right here. Number four is Eagle at Microsoft Azure in the Seattle area in the US. Number five is HPC 6. It is in Italy and is again equipped with AMD MI250X GPU. Number six is Fukaku. This one is quite a special one because it doesn't have the GPU. It is a pure CPU machine. It is ARM CPU. Number seven is ARPIS in Switzerland, and it has NVIDIA GH200 GPU, NVIDIA GH. And number eight is Lumi. It is located in Finland, where Young works there. It's the AMD GPU, MI250. And number nine is Leonardo. We always call it Leonardo Booster because we are quite familiar with one. It's equipped with NVIDIA A100 GPU, and last year we used this one for our training. So this year we also have this one. Probably next time for this Julia high performance data analysis, we can try to use this one to use the NVIDIA GPU. Number 10 is Tulumi, is in the United States. Again, is Lawrence Livermore National Lab. It's against AMD GPU. From the list, you can see that for this top 10 HPC class, 9 of them are equipped with GPU. So GPU is so popular, and the GPU can provide the powerhouse for the scientific research and also for the others. Yes, we talked something about GPU. So what is GPU? We all know that the CPU is the central processing unit in our computer. For GPU, it is a specialized electronic circuit. GPU was originally developed for computer graphics and image processing, and now GPU are evolved to general purpose accelerators for massive parallel computing. Last month, we delivered a workshop on GPU programming, and the recorded videos and the lesson materials are available right here at the shared hacking document. You can come to this link right here. And in addition, we had delivered 2 practical intro webinars for GPU programming using Python and Julia. The recorded video is just for 1 hour, and the materials for the demo is available right here. So come to this lesson materials if you are interested on this aspect. Now here, I'm not going to talk too much about the GPU programming. You can come to these lesson materials. Let's get back to the Julia topic. So for this, why Julia for HPC? And can Julia effectively or efficiently use features of HPC resources for the scientific computing? We will see here. For traditional language, we mean traditionally in the last 1960s, 1970s, the package were developed using Fortran and C. They can generate a machine code with quite high efficiency. This means that they require the software developers can have a good control of the memory issues, and therefore this leads to some kind of low productivity. Means that you have to take care about the memory issues. Otherwise, you can get some severe problems, for example, memory leakage of things. And in addition, the porting of the software from one cluster to another cluster, you might come to some problems. For yeah, from Linux machine to the Windows machine or to others, and also sometimes depend on the compilers. You can see, but for the code written in C and Fortran, it's quite fast, but it's very hard to control. On the other corner, it is Python and R. They are representative of dynamic and interpreted languages. They can easy to learn. You all know about Python and R, so it's just a human read, and the code is quite easy to understand. But sometimes it's difficult to generate efficient machine code. Means the efficiency is not so high. Take an example. If you have a code, you run this code just for 1 minute. It is okay. Just click the mouse and wait for 1 minute. You can get the result. But if you need to run this code for hundreds of thousands of times, or you have a lot of code and it takes several weeks or even several months to get the result, and then you may consider to speed up the computation and to consider the performance of your code. Julia is at another corner right here. It's a combination of these 2 categories, means it is fast and some kind of easy to learn. We have mentioned a lot of features of Julia. It is open sourced, it is fast, it's highly composable with natural syntax for scientific computing and also for the memory management. And the Julia code can generate efficient machine code with the JIT technology, means JIT is just in time. And for parallel computing, here I mean parallel computing, or I mean multi-threaded computing, distributed computing, or even, for example, using MPI, and also for this GPU programming. We will cover this aspect in this workshop. Another thing is that Julia can direct interface with the libraries written in C and Fortran. Yeah, well, all the code, you can say, with the same overhead as calling them directly. And which means that there's no extra overhead if you use the library written in C and Fortran. And there are also some other packages for Julia to interface with the other programming languages, for example, R, MATLAB, and also Python. I will cover this aspect at the last day of this workshop. So as we mentioned something about the parallel programming, let's talk something about the parallel programming using Julia. There are several types of parallel programming in Julia. The first one is asynchronous task. It provides the ability to suspend and resume computation for input and output. But this is not so specific to HPC usage, and therefore we are not going to cover this aspect in this workshop. And number two, multithreading, which provides the ability to schedule tasks simultaneously on more than one CPU core with shared memory. Yeah, the machine with shared memory. This is the high. Julia can implement the threading for this base thread library. Yeah, this library quite easy to use for this multi-threading. And you can this one for this multi-threading computation. For the distributed computing, which refers to the running multiple precise with the separate memory. This machine is somewhat different to that one. The previous one is with shared memory, where you use multi-threading. With a separate memory, you distributed computing, which means that there needs to something about data transfer from one node to another because they're not shared in the memory. So Julia implements a construct for distributed computing in this distributed library right here. There are also some external packages such as MPI, MPI.gl, you see right here, GMI bindings for the message passing interface. These are also available for this distributed computing. As I mentioned in the afternoon, Pedro from HPC2M, we talk about this multi-threading and distributed computing using Julia. In addition, we also have this GPU computing, which ports the data-intensive computations to the GPU part on either high level or low level programming. The general procedure is that we can generate something from the CPU side. We transfer the data from CPU to GPU, and the launch the kernel, or launch the kernel is the code function from the GPU side, and to do some arithmetic calculation and to get the result. And the next step is fetch the data from CPU to GPU and then finalize this process. And here we can just we can cover this GPU computing, distributed computing, and multi-threading this part. So yeah, if you come to this specific episode to learn this aspect. And here we also provided some reading materials. For example, the Building HPC community, we have the Julia programming language, and Julia the Petaflop Club, and MPI.gl, and the high-level GPU programming in Julia, and some applications of Julia for this data science and machine learning project. So take your time and to go through these materials if you are quite interested on this aspect. And yes, this is quite the motivation part. We're going to highlight the importance of Julia and their application for this GPU programming. Any questions? If no, I think I will continue about the second episode. It's the writing performant Julia code. I have something right here. Yes, writing performant Julia code. We got to know the basic syntax of Julia. And in this episode, we will work on a small project. I mean, small project means that we can run everything in this project and do some extra things for the benchmarking and the profiling the result, and also for the data visualization. What we want to get from this project is how to measure the performance of a code if we have the code in this project, and how can we profile the Julia code, and which part is the most time-consuming part in this code. And if we use Julia for this project, are there any pitfalls, performance pitfalls, and can we avoid these pitfalls in this programming? Yeah. Let's introduce this toy example right here. We consider a discretized Laplace operator, which is widely used in numerical applications to solve many physical phenomena. Here we just use a 2D example, yeah, XY direction. For the formula is given right here. We discretize this system into a lot of small cells right here. The value of the central cell is dependent on the values on its four neighbors: left, right, top, and down. And just here it's quite simple. Just take the average of these values of the values for these four neighbors. And if we have a 1D, we might just consider two cells nearby, either left, right, or top, down. This is quite simple. For 3D, we might consider two extra neighbors, either from the front of this plane or the back part of this plane. Yeah, this is the description of this Laplace operator. And in Julia, the code is implemented as this. We need two arguments from outside, and then we know the name of we know the size of this argument. That is the size of the physical system. Most relevantly, more pertinently, that is how many cells for this x direction or y direction. We need to know this number, and then we use a double loop to calculate the values for each cell at the inner part, because we don't care about the outer part, at the outer shell, that's just the inner part. And then you doing this simple arithmetic calculation. You can see it's just the addition and also the multiplication. Yes, now we know how to do the calculation. We can set up the physical system. That is the numbers of cells at each dimension. Here we just for x direction, y direction, which is 4096. But during the exercises, I use quite a small one. You can see here, I use 2048 just to because I use the personal computer for this computing, that I can get a quick result from the computing. And also, we set the values for this cells at the outer shell. Means we just care about the cells at the shell part. We give an arbitrary number. This is 10.0. In the computation, I use 2.0 because in this one, you might can get the clear image of the distribution of these values in a quite short time. Yes, after setting the physical system, we need to run the computation here, and let's just say 1,000 steps or 2,000 steps, depending on right here, depending on what you want to see. And then once we get the result, we can visualize this result and using where it is using here, using the heat map function method that is provided in this plot.gl package, and to visualize the computational results. Yes, and this is the code of this project, and everything is right here. And for first, we define the physical system. We mesh the system to set the size of fine grain the system so that we can get the specific size of each cell. And then we initialize the values for all these cells. We run this computation for 1,000 or 2,000 steps, and then we visualize the simulation result. That's it. This is what I have got last night about this. Define this function is here, run this function. Here, Laplacian 2D exclamation mark means this. I need to mutate these two argument in place. And then set up the system, number of cells at each dimension, and give the initial values for the cells and outer shell, and get copy this one to a new matrix. Setup is here, and the setup gets this from the to these two universal matrices outside, and then we use this pkg that plot. It's here. Add this one using pkg package manager. Add this plot.gl package and use this one to visualize the computer result after we run this computation for 2,000 steps right here. And I did not, I don't know why, because I run this computer, another computer. If you see, this is the result after I run this 2,000 steps. And this out shell, this is the value is 2.0. It can see the gradual evolution of these values from the outer shells, the cells and outer shell to inner part. If you use quite a small system, let's say 256, 512, and set value to be 2.0 or 1.0, you can visualize the very good distribution in 1,000 steps. It's very good. I have prepared this example. If you're going to use Lumi for the exercise, you can directly run the script there, and after maybe 5, 6, 7 minutes, you can get the results. And I will show you later how to visualize this result from Lumi. Yes, this is the code part. And we know that the code works. And the next step is that we want to benchmark this code. We want to know the performance of this code and which part is the most time-consuming part, or which expression is the most consuming expression in this code. For Julia itself provided the at time macro. Yes, they can measure how long it takes to run the code, but this value is quite rough and it's not just for how long it takes to run the whole code. You cannot get an accurate value for specific expression, specific block, for example, the for loop or while loop. So we recommend to use this package called the benchmark tool of GL. It provides the macros to perform the benchmarking. And there are two macros that are quite important for us. This one is B time, is the benchmark time for quick syntax check. And the second one is the benchmark. It runs a full benchmark on a given expression and then give us the feedback, how long it takes, and if this expression is the most time-consuming part. If it's the first time for you to use this benchmark tool, you should, for example, add the use pkg, means package manager, pkg add the name of this library, and then use this library, and then run this expression like this, benchmark, and then the function. You can also capture the output using benchmark right here. We use another tuple to save this result and the type of this tuple, and get the minimum value from this result. Because we we run this one evaluation with lots of samples. Let's see the result from here using PKG because previously I use PKG right here, so there's no necessary to use comment right here. PKG add the benchmark and using benchmark to benchmark this code. You can see this is what I got last night. Means this range for one evaluation we have 1,555 samples. Means we have got 1,555 values time from this evaluation. And what about their distribution? From here to here is from mean to max, it's 3.118 millisecond, and the max one is 3.6 millisecond, and the medium is 3.142. If you take the error bar thing, it's the mean, the 3.136 plus minus 54 microseconds right here. And if we want to know what is the minimum time to run this code, it's 3.122. This value is right here. And yeah, this is the one we are going to extract it from this one, and we can use this one for this result of this benchmark. Yes, and here we know the results and we know the benchmark of this code. Yeah, this code works, and we know the efficiency of the code. And how can we know which expression or which block is the most consuming one, or how long it takes for each expression to run from the in the code? And we need to use the profiling module that is the part of the base library, which relies on the sampling code, gathering statistical information on where the time is spent when we run this code. Profiling is super important for identifying the bottleneck of this code. And here is the result. I will I will describe something right here. Yes. Yes, I add this profile.gl and using this library, and then profile initialized delay, because if I do not include this one, I might come through some error. It need me to prolong the simulation. I don't want to. I just want to get the result from a relatively short simulation to see what I can, which part is the most time consuming part. And then this is the tree-like structure. I got this. Can you see this right here? Yes. For each line, it represents a particular spot in number in the code. It means and the overhead it takes. And the indentation indicates the nested sequence of a functional call. With more indented lines, you can see these much longer lines, indicates the being deeper in the sequence of this call. In each line, the first field right here is the number of samples taken in any functions in this line. And the second is this package right here as the name of this file and also the numbers of this line when we sample this code. The third is the function name right here. Oh, this is the name of this package, and this is the name of the file we're going to call. It's been noted that the C-respective line numbers may change as Julia code change, or here I use the Jupyter Notebook for the running. If you use VX Code, you might get varied results, but the conclusion should be the same. And here we can see, maybe we know nothing about this, but if we can see that for the first one, we have a Julia raw argument. There are two arguments we need. If we know the code, we know where it is. We need two arguments. One is you, the other is you new. Yes. Then this corresponds to the first one. And the second one, event loop. We from the name we can just figure out it's quite simple. This corresponds to the double loop. I mean double two loops to get to calculate to make the arithmetical calculations for each inner cells in this physical system. And for the others, maybe not easy to figure it out, but from the last one, we can see that the get syntax and the set get index and the set index is the most consuming part because the overhead is one. There's no other overhead for the other steps, and this is the only one where we get the overhead. Means this get index is the most consuming part. So what is get index? If we come back to the code, for the I can use this one. For the code, if we want to calculate the value for the central cell, we need to know the ID for its neighbor, left, right, top, and down, and then extract the value for each neighbors, then do this arithmetical calculation. So how to get the ID of its neighbors, and this should be the most time-consuming part, because for each cell, before you do this calculation, you have to know that, okay, my neighbor left, right, top, down, who are they, and then get the numbers. For each calculation of this cell, you have to repeat these steps 4 times, and because we have 4 neighbors right here. So yeah, this is just straightforward. This is the most consuming part expression in this code. And if you make run this code for quite long, like hundreds of thousands of steps, and you have a large query system, and then you can visualize, you can get the quite clear that not only the get index but also the set index. Yeah, sometimes one of them, sometimes both of them will be the most consuming part for the computation. And we know this, so can we handle this, or how can we solve this bottleneck thing for this code? Yeah, think more about this. And we come to the next part of the profile view. Here is not so easy because I got something right here. Theoretically, if I can get something fire flame graph thing, that is quite beautiful, and you can visualize how long it takes and which part is the most consuming part. But here it's not so easy. One thing is that in this code, we have quite simple arithmetic calculation, addition and multiplication. We don't have complex calculations right here. And another option that you can use VS Code. If you use VS Code, you should change the code to something VS Code server dot add profile and then the name of this function. Then you can get something like this. And here is another example, most time demanding example. I can come to this one. Yeah, it gets some results like this. And from here, you can figure out which expression takes how long it takes for each expression, and which expression is the most consuming part from trial running. Yeah, Here I'm not to cover this aspect anymore. So if you use VS Code to run your code, VS Code to run the code example, show me the result, and we're going to uh, share with this result with the others. Yes. Now it is we can say that this is small project it is done. What is done is mean that we proposed this toy model, we have this code, and this code works. We can get the correct results, and we know the benchmark and we know the bottleneck of this code. If you run this code for your project, it is okay. But if we want to think more about can we improve the performance of this code? If yes, what we can do and how we can do to improve the performance of the code. Now we are coming to a upper level and to think more about how can we optimize this code so that we can get a very good efficiency or good performance of this code. If we run this code one time, it is okay. Just maybe take 1 hour, take 2 hours. If we run this code for thousand times, you might come to it takes more than several months to get the result, to get all this result. Then you'll be quite a struggle about this, um, especially for the scientific research. If you can publish these results 1 month, well, probably can get something new. And if the others want to publish these results, but they are late, well, they can well publish somewhere, but maybe not high impact like journal like you. So think more about to improve the performance of the code. There are several options to doing this code optimization. Here we just mentioned some. The first is column major orders, column major or row or major orders. This we all know that the data in multidimensional arrays are stored in different orders depending on the specific programming language. For Julia, it is a column major order. That is that arrays are stacked one column at the time in the memory. Means whether we read data, we write data, it will be the column major orders. This is similar to that in Fortran, MATLAB, and R, but this is totally different to that in C, C++, and NumPy. For C, C++, and NumPy, they are row major. Yes, if you know this, you will figure out that the procedure for reading data from a matrix has a significant effect on the performance of the code. This is come to the memory level. We have to know how to control the memory. In this example, we here is just a swap the two index I and G, and yes, swap these two index in the double loop, and later you can take your time to run this code, to benchmark this code, and to see what you can get, better performance or worse performance. Let me know. I will show you my code here. From previous part, you can see the benchmark is 3.1. You know this number. If we swap the index, IJGI, then doing this benchmark, it is 38, 10 times slower. Is this the expected? Or yeah, run this code later and show me the result. We can make a comparison. Number two is about inbound macro. This macro eliminates the array bounds checking within the expression. This can save some time if you run this code. and we add this macro. We just add this macro in bounds to the inner loop and then benchmark this code and to see how long it takes to run this code. The result from my test is right here, 1.9. It's about 2 milliseconds. You know, the previous one, it's 3.1, and now it's 1.2. We can get some speed up, like 1/3 thing. Wow, super good. And if you run this code, let me know what is the number you get, and either using Lumi or using your personal computer. There's another tip for using the static arrays instead of using the regular arrays. For applications, we have many small arrays or vectors, or we can say metrics. You can get this benefit if you use a static array instead of using normal arrays, because this one, okay, right here. This example here, it may be not so relevant to this or to our projector here, but you can take this one as a code example to see what you can get. If we use as array, yeah, this is M1, this matrix generates a random matrix with the size 10 by 10. Number two, M2, we just generate this array, this matrix using this as array, means a static array. We will see what we can benefit from using this as a static array. If you run this matrix multiplication, for the first one, it's 311 nanosecond. The second one is 100 nanosecond. I did a short test right here. You can see. For the first one is 200 nanosecond, and the next one is 80 nanosecond. Yes, seems good. And that means that you can get benefit if you use a static array like this. In addition to this, there are also some other tips to improve the performance of the code. If you come to this Julia's official document at here, there are lots of code examples right here. And if you are enthusiastic about Julia programming, yeah, take this and to see you can get a lot of benefit if you can put this into practice, and it can make your code much to run much faster and much more efficiency. And here, for me, I'm not going to talk too much, and there are lots of tips right here. Go through these materials someday, or if you are really want to use Julia for in your project, or you want to port your code from one programming language to Julia, and pay more attention to this aspect. Yes, then we are coming to the exercises. We can take time to run the code example right here. Not only the inbound to use the inbound macro, but also from beginning for the how to run the code, benchmarking, and then the profiling, and then optimization options. It means either the row major order or the column major order, and the inbounds, and the other tips. You can think more about this. How to run this code? If you're going to use Lumi, here is the command right here. CD to this scratch the project and create a directory for you, and then come to your directory, git clone these lesson materials from the website to Lumi, and then cd this content code performant directory right here. I have prepared everything there. So at the first step, you can bash this script to see Usually it take several minutes. You can get the result. After you run this result, you will get a PNG file, and later I will show you how to visualize visualize this PNG file in another login. If you're going to use your personal computer, you have installed Julia in your personal computer, you're going to use your personal PC to run this code, it's also okay. You can just git clone lesson material to your personal computer and unzip uh, this material somewhere and come to this folder performant. There is a Jupyter notebook which is called performant example. This is the one I prepared last night. So you can use this one and to run this code and then make changes on this Jupyter notebook to see what we can get. Let's have a match about this. This is the efficiency I got last night. The number of cells for each dimension is two-dimensional case is 2048 for X and Y. I run the 2000 steps. The value for the boundary cells is 2.0. And for the benchmark result, at the beginning it's 3.1. And if I change the swap index for A and G, then it's 38. If I use inbound, it's 1.9. So other tips, PC means I use my personal computer for the computing. If you use your personal computer, you can address PC. If you use Lumi, you can address Lumi right here. Let me know what you get, and then we can see something interesting.
Okay, so we will talk about multithreading in Julia. Yes. And the first thing that we will see is that there is already some implicit parallelization by using multithreading in some linear algebras, right, that are used by Julia. For instance, if you're using open blast libraries, yes, you can get some parallelization without modifying your code. And the only thing that you need to do is to set the environmental variables, right? And there are some ways to do that. So you can set the number of threads inside a Julia session or a Julia script, for instance, by using this function, right? Where you specify the number of threads, or you can set that in your bash environment or your batch script when you export, sorry, this variable open blast num threads and the number of threads that you want. So here there is an application of that. So you need to import the linear algebra package. And then here you define two matrices of some relatively large size. So this will work especially well for large matrix sizes. Otherwise, there is some overhead that is created, right, by the number of threads. So, and then here there is a single thread operation, and here one is timing the multiplication of the two matrices. And notice here that one sets the number of threads inside the Julia script. Yeah? And here one uses all the CPUs that are available on the allocation. Right? If you requested some number of CPUs or cores, then this will make them available in Julia. So then you can see how this behaves, right? When you increase the number of threads, and you can get some optimal number of threads by using this approach. For instance, here I wrote or copied this script for linear algebra, right? So you can see here that I use the same size of the matrices, and then I am timing here, yes, this execution for the matrices. So then, let me see. Then I can run this script, right? So one can prepare this script for Lumi, yes, by using the current project. They will load the modules that are specified in the prerequisites. Then you load the Julia, right? And here I did some previous runs to test this environment. So here you specify this Julia, right? And the name of the script, Julia script. So then notice here that I am specifying 6 CPUs, right? So I can reduce that to, let's say, 2 in this case to make it shorter. So it does take a long time, but even in that case, it takes some minutes to get accepted, right? To start running. And because of that, in the previous example, in the next examples, I ran the code previously, right? So I will show you the outputs. So, and by doing this, you can see the difference between running with a single thread and also using multiple threads. So again, notice that you don't need to change your code yet. And the only thing that you need is some external variables or some way to set the variables, as in this case for BLAS, right? So, but this is an external or implicit parallelization that is included in the linear algebra. Yeah. Besides this threading approach, let me see if it's running. No, it's not yet running. So, but besides this parallelization approach, which is based on OpenMP, so if you are familiar with OpenMP, this BLAS threading is based on OpenMP. So besides this parallelization scheme, so Julia also offers you some threading approach. And this can be, well, at least it was confusing for me at the first time that I saw that, because I thought that these Julia threads were the same as these threads, but they are completely different. Yeah? So Julia has its own mechanism to set the threads, and this can be activated with the environment variable, this one Julia num threads, that can be used in Julia to set the number of threads. Let me see. Yeah, it run, and let me see the output for the linear algebra case. So you can see here that if you set the number of threads to 1, it took about 35 seconds. And if you use 2, it took about half. But it's not exactly half, because there is also an overhead for when you create some threads. Yes, and OpenMP needs to handle this extra overhead. Yes, right. So that's why it's not perfect, and also it depends on how many processes are running in the back end of the architecture and so on. Okay, so I was saying that in Julia you can set the number of threads, but these are called the Julia threads, right? And this can be done externally with this environment variable, or also you can use the my -t or dash dash threads, which has essentially the same effect as using this environment variable. So for using these threads, you need to import this library, right, in the script called base threads, and then this will give you the threads, yes, that are set in the system. So one way to check the number of threads that are available is by using this function, threads, right? And it will print out how many threads are or are available for computation. So, so there could be some issue, and you need to figure this out. So imagine that you are using one of these libraries, right? Linear algebra. But at the same time, you're using some threading mechanism that we will see right now, yeah, in Julia. So in this case, if you set some number of threads and also you set some number of threads for the open blast, for instance, then you will multiply the resources, yes, and you need to be aware of that when you allocate the resources in your batch script. Yeah? Otherwise, you will be oversubscribing the resources. So there are several approaches to deal with multi-threading in Julia. You can use this macro threads that is available on the base threads library to parallelize a loop, right? This is especially good for parallelizing loops. Also, you can use the span and sync the macros to synchronize and to deal with the task on the threads. Yes. And you can also use the span and fetch. And this is used for more flexible workflows, right? These are more used for rather static workflows, but this one can be used for more complex workflows. Here there are some examples of how we can use these macros. Yeah? So in this case, we are performing a for loop. Yes. And here is convenient if you use the threads that the workload for each thread is almost the same or is very similar, right? In this case, the threads macro is the preferred option. So you can also use for more flexible workflows the sync and spawn macros. So in this case, for instance, we can partition the tasks that need to be done, and we can create the so-called chunks, right? So that each thread can solve one chunk of them. And then we iterate over the chunks, yes? Not over the iterators as in this case, right? But rather on chunks of the data. So this is more useful, yes, when you deal with this spawn and sync. So spawn will generate the tasks, right? And notice here again, it's preferable to use chunks of tasks. And then this macro here, we synchronize all the spawn threads at the end of the for loop. Yeah? In this case, the chunks or the chunks of job that need to be done can be a bit different in size compared to this one, where we said that it's preferable to have all of these tasks even or that take almost the same time, right? But in this case, it's more flexible. You can solve several tasks, and maybe they don't last the same time. Yeah? But for more complex operations, right, it's prefer to use the spawn and fetch. For instance, if you need to start some task, but you don't need the results immediately. So you can wait for the results some time while you are doing other types of calculations. In that case, the more flexible setting is spawn and fetch. Here, spawn just generate the task, and then just when you need it, then you can fetch the data. And this is called asynchronous computation. Yeah? So here there is an example, and you can run this and see how is the performance of this code. So here is a serial function for computing the square root of the elements in an array. So this macro here is for avoiding checking the borders of the array that Julius does by default, right? So this can improve the performance. And if you know that the iterator is within the range of the array, then it should be fine to include that. Yeah? So then you compute the root square of each element, and you store that in a matrix called B of similar size, and return the matrix B. So how will we solve this serial problem by using the threaded approach in Julia? So we call the base Julia threads. And then we need to do some modification to the function, right? So we call it threaded sqrt array. And in this case, notice we put a decorator on the iterator. We said that this decorator is useful for fixed loops, right? As in this case, where we know the initial and the final value for the iterator. This is very useful, and also for even distributed works. So in this case, we are computing just the root square on each element. So this is even distributed across all the iterations. So that's why it's convenient to use the threads macro. But we can also use the spawn and sync macro, this combination. And you can see here that we need to refactor the initial code, yes, more drastically than in a threaded approach. So for instance, we need to create a function that instead of the iterators or the isolated iterators can perform the task based on chunks, right? So we divide a rank into pieces, and each piece is called a chunk, and then we can perform the root square just on this chunk, right? So then we create a new function called threaded sqrt, and then we initialize the chunks by using the iterators partition method, yes? And this will give us a chunk. And here we can use the spawn macro to generate the tasks. But notice that this function now has these arguments, A and B, and also the chunk size. And previously it only had one argument. Yeah? So we refactor the code even further. And finally, we synchronize the threads and return the matrix. So here we can see how is the performance, right? Based on the initial sqrt array, and also based on the sync and spawn macro. So here I did some previous calculation. Let me see. Threads. Yeah, here. So you can see here the functions that are in the website, right? This is the sqrt array, and it takes one matrix only for the serial case. Here, in this case, is the sqrt array, which takes the two matrices and the chunk as arguments. And here there is a threaded function, right? Based on the threads macro. Here is the sync and spawn. macro combination. And also we can do some fetch and spawn combination for the macros that I showed you before. And here I am doing the benchmarking, and here you will need the benchmark tools package, yes, besides the base threaded package. So then I compute the serial mode, the threaded approach with the threaded macro, the threaded approach with sync and spawn, and then this one, the fetch and spawn. And here I just say if the results are correct. Yes, this is a way to check if the results are correct based on the serial case. Right? So I run this code for this particular matrix size. Let me see, it's here. And you can see here the performance. Yeah. So it took 2.7 milliseconds with a serial case. This was the performance with the threaded macro. This was the sync and spawn is lower than this one. Notice here. And here is the fetch and spawn, which is the slowest of these three. Okay. But even though this is lower than in the serial case, but yes. And the results were true in all the cases. So you can see how the performance is compared, and for this particular case, because the task last almost the same time as we said before, the spawn and fetch is not useful because it creates extra overhead, right? But imagine that all the tasks are not or do not last the same time, then this could be a useful method, the spawn and fetch, right? Because it can also help you to do other things while you're waiting for the result. So the EULA thread has an overhead, yes, of some microseconds, yeah, and you will see some benefit from the threading approach when the size of the problem is large enough, yes, like large matrices. So if you work previously with other languages that support multithreading, for instance, OpenMP, you will see that Julia multithreading has the same problems, yes, as other threaded approaches. In particular, the race condition, yes, is present because here all the workers want to write over the same data, right? And then the data is not useful any longer. So there are ways to correct these issues, and the approach that is taken in Julia is similar to the OpenMP. You are familiar with OpenMP, where you can use atomic operations, right? And in this case, for more complex problems, you will need most likely to refactor your code, right? So the initial version needs to be refactored drastically, most likely. So here there is an example you can see here. There's a square summation that is done. So you take the square root of the elements, yes, of an array, and then you add them to one variable s. Yeah. So this variable is initialized to 0, and it has the same type as the matrix A, and is given by the L-type method. So this will run over each index of the matrix A. So notice that if we run this code in serial mode, there is no problem because there is only one process that is executing the for loop. and that is accumulating the result in this variable s. But the problem arrives when we have several threads, right? As in the present case with the race condition, where you initialize, as we did previously, some variable s that store the summation, but then we decorate the for loop with the threads macro, yes? And then we try to write over this variable here. So if we have several threads, they will try to write over this on this variable, and this will cause the race condition, and the value the variable s is meaningful. Yeah? It is not meaningful. Sorry, it doesn't. It is not useful. So that's why there is a problem here, and we need to figure out how to solve this race condition, right? And one way to do that is by using the atomic operations in Julia. And the concept is similar to OpenMP, if you are familiar with OpenMP. So here we define a new variable or a new function called threaded SQRT and doing some atomic operation. Then we define an atomic variable, notice here, atomic variable of the same time, and it's initialized to 0, yes. And then once we have these atomic operations, we proceed to do the macro with the threads, yes, the macro from OpenMP, yes, sorry, from Julia. And here we compute the addition by using an atomic operation in Julia, which essentially limits, yes, the writing ability of the threads on each value, on this value s, so that only one thread can update this variable s. And this avoids the race condition. But in this case, if you run this code, you will see that the performance is very, very, very bad, right? Because this atomic operation is expensive. Yeah? So although we are solving the problem, this problem here of computing the root square of the matrix elements is so lightweight that is not worried to add the atomic add operation. So we would need something more expensive, yes, so that the overhead of this function is not that much. But for only this part, this computation here, root square, that is not doesn't compensate the atomic operation. Yes, in this point. However, we solve the problem, but the code is very slow. How to improve this? So we can go further and try the following. So we use also the decorator, but in this case, instead of a variable, right? Instead of a single variable s, as in this case, we use an array. Yes. Maybe this is one of our ideas, to use an array. And then this array it has some number of elements equal to the number of threads. We think that based on the thread ID, yes, if we have some number of threads, each thread has a thread ID, and then we can use the thread IDs to allocate the partial value on this partial array, right? So, but although this can solve the problem, the issue is that the threads during the runtime can migrate, yeah? So, which means that if one thread is sitting on a physical core, right, it can move to a different one, leaving this value of partial array inconsistent. Yeah? So the value is not well updated, and that's why you will get unuseful data for the partial array. This is called train migration, and it occurs also in other approaches like OpenMP. Yeah. And we solve the problem again, but the problem is that this migration can occur, leaving the results unuseful. So what then can we do to solve this situation? So here there is a workaround, and this is more complex as the initial code. You see that the initial code that looks like this, when you go for parallelization, you need to figure out how to refactor that in such a way that the parallelization is supported. So here, for instance, we have now a function called sqrt sum, and it takes a matrix and a chunk size, right? So basically here we are not working with this isolated iterator values, but we are working with chunks, yes, or ranges of the iteration values. So then we collect the summation in this variable, and notice that because this is inside the function, this is a private value. So it's not seen by other threads. So then we define the sum workaround, and we divide the entire range or the entire workload by using this function here, partition, and this will create the chunks. And then here in the chunks, we can then create the task, right? To generate the sqrt function, solving the part corresponding for that chunk. Yeah. And finally, we can do this reducing operation, yes, where we collect the partial summations, and then we get the final value. So you notice here the refactor code. It's a different idea, because here we are not working with a single iterations, but we are working with chunks and also distributing the chunks, right? And creating the tasks here. Yes, and then reducing the partial values by using the map reduced. So this is what we have seen. The slow version is correct, and this is a good point to start, right? Only when your serial version is correct in Julia or any other language. Once this is correct and is giving you the good results, then you can try to improve this serial version or even go for some parallelization. Otherwise, if this one is not working, it would be a nightmare to start parallelizing that, and you don't even know you have the correct result, right, in serial mode. So now this is working. Then we go for parallelization. We try the first approach, and we realized that there was a race condition. Then to solve this, we apply the atomic operation. And this, in the particular case for this example, is very slow, because we had to compute just the root square, which is well optimized in Julia. Right? So the migration version is still incorrect, yes, because sometimes it can give you the correct results, but other times not, depending on the thread migration. And the workaround is fast and correct, but it requires some code refactorization. Yeah? So here there are two questions. What does L type do? And also what does each index do? Yeah. So you can think about this based on what I mentioned previously. Yes. And notice here that we said that this macro is straightforward, but we also need to take care, yes, of how the data is managed, yeah? In particular due to race condition, yeah, and other common problems that are available in trading mechanisms like trade migration, force sharing, right? And so cash misses, but this is more complex. So these are two exercises that we will give you, yes, and we have some time for that. How much time do we have? 30 minutes, Jonglei.
Please.
Yes, I will start this part for distributing computing. In the previous lecture, we saw the multi-threading approach, right? And this is useful when the threads just can share some memory, and because of that, they have easy access to that memory, which is fast enough, right? But this process is scalable only up to the number of cores on a single node, for instance. Yeah. So currently, for instance, there are some architectures that contain up to 128 cores, right? And they can share some memory. And in that case, you can take advantage of multi-threading. But if you want to go beyond one node, yes, then distributed computing can be useful. So here we will take a look at multiprocessing and also shared arrays. So notice here that the distributed is general because it can help you to scale your code up to beyond one node, as I mentioned, but it can also help you to scale your code inside the node, following a shared approach as in the multi-threading case. But in this case, you will need the shared arrays package. So distributed computing. Here we have processes. Notice the nomenclature in this type of computing paradigm, and we are calling the workers processes, yes. And in the previous case with multi-threading, we call them threads. Yeah, so we need to distinguish these two things here, yes. So in distributed, we use processes that need to communicate with each other. And if you're familiar with this type of communication, you will see that it has some common features with message passing interface, MPI. Yes, that this is a standard protocol for sending and receiving messages. So, but Julia has its own implementation of the message passing, and this is contained in the distributed module. Yeah. So, uh, so you're familiar with MPI, right? And you are thinking about the same paradigm of sending messages, receiving messages, broadcasting messages, right? So then this is different from the way Julia performs the distributed computing. So in MPI, we have two-sided communications when we deal with sender and receiver processes. So this is a two-sided or point-to-point communication as in the MPI nomenclature, right? So, but in this case of the Julia concept, this is more like a one-sided, right? Where we send something, but we are not expected that message to be received, or until some point that message or that data can be used by any other process. So we are not expecting a sender and receiver, but on the other hand, we are dealing with the so-called high-level parallelization, right? So, and this includes some higher level operations, right? That are not implemented in the way as send and receive in MPI, right? So here you can send uh, uh, pieces of work or data, right? Or operations that can be executed on some available process. So this is more like one-sided, right? We don't need a message send and receive. This is the main idea in distributed computing. So this can be useful if we don't need to specify or be very specific as in the case of MPI. Yeah? Because remember that in MPI, if you want to do some MPI parallelization, you need to specify, for instance, the type of data that needs to be sent, the type of data that needs to be received, the counts of the data to be sent and received, yes, the buffer size, and so on. So this is handled by Julia internally, right? And that's why it's called a higher level operation. So you need to be explicit about that. Yeah? So therefore it can be it can handle more complex situations than in the case of MPI. So distributed computing is useful if you want to scale your code beyond a single node or even on a cluster of machines. Yeah, this is also possible. So here there are some references that you can look at, right? And yes, they will provide you more insight about the distributed parallelization in Julia. So here is the way to start Julia, right? With some workers. Notice here the difference. Workers is different than processes, yeah? And we will see that right now. So we can start some number of workers, right? By using the -p option. And here, this is the way to start the number of workers, right? And this is a script that will show you how it works. So you don't need to install this package because it is shipped with the Julia standard library, and this will print out the number of processes. Notice the difference: the processes, and also we have the so-called workers. Yeah. So how does it work? So initially there is only one process, which is the master, and then we can add some other processes. In this case, 4. Yeah. So if we print out the number of processes here, this will give us the number of processes that are running in this case, right? And this will be the number of workers. So the number of workers is the number of processes minus 1. Yeah? Minus 1 because you need to consider that the master process, yes, is not part of the worker space because the master process is reserved to handle the communication across the workers. So here I wrote one example. Here distribute. So basically here I print out the number of processes available, right? Also the number of workers. And then at this point, I added 4 processes, print out the number of processes, the number of workers, and this instruction here can be used to remove the worker processes. Yeah. And here, let me see the outputs. I ran that previously. Distributed out. Oh yeah, here you can see that I started the code, the Julia code, with the dash p equal to 2, right? The one that I put here, dash p equal to 2. But notice that this is the number of workers, but the number of processes is the dash p, 2 plus 1, which is equal to 3. Then I printed out the number of the workers, which is 2, yes. And then here I added 4 processes, right? But because there are already 3, yes, so then I will have 7 processes. And how many workers is just the number of processes minus 1, which is 6 in this case. Yeah? So pay attention to this feature in Julia, number of processes and number of workers. And remember that 1 is reserved for handling the communication of the workers, and eventually can take part into the calculations. Yeah? So here is how I run the code, yes, with the batch script. Here I need to specify if I will deal with 7 processes, I need to write here 7, yeah? Just to make this optimal, right? Otherwise, if I write 6 or 5, then I will have less CPUs than processes available. And if the master process, for instance, is very busy and it is doing something complicated, then you can see some performance issues in your code. So consider that you have the processes and the workers, which is the number of processes minus 1. So if you want to run your code, right, or to parallelize your code across multiple machines, this is possible with the dash machine file, similar to the one in MPI. And this works with a passwordless SSH communication if the cluster where you're working supports this type of communication, right? There's also a package called Cluster Manager that is included in Julia. And depending on the cluster, this can be used, right? Especially for this type of communication which is not always allowed in the clusters, I would say. So here the processes has an identifier similar to the thread ID that we saw in the multi-threading approach. But here we can query the process ID by using the myID function. Yeah? And the myID function has the value of 1. Yeah? So here we can use this macro, spawn ads, to put or to transfer some work to a specific process. And here there is a concept, right? It's called a future that is present in other languages like R or Python, right? And essentially it means that you will place, yes, some calculation in the process that at some point in the future, as the number suggests it, yes, it will be executed. But it is not obligatory, compulsory, yes, that it needs to be executed right away. And that's why it's called a future. And it's useful, for instance, if you don't want the results to be available immediately, but you can do some other work in between, and this can help you to optimize your workflow. This is useful if you have complex tasks, right? Not the loops, for instance, because the loops are static, yes, and in general they are evenly distributed for the workload. So what if you have different processes? Imagine that you need to write some files, then you need to process those files, send the output to another program, and so on. If you need several tasks, right, that are not even distributed, they don't take the same time. So then you can use this spawn at. Yeah? And in particular, in that case, we are using spawn at to send this function to the rank two, to the process two, sorry, the process two, and this will just print out the rank, yeah? And a random number, yes. And finally, just when the results are there, you can fetch the results and then you can handle the results at this point. But in the meantime, notice here, you can do other types of operations if you need that. So this is a higher level construct, yes, span out, right? And there are also other constructs available in distributed computing. For instance, distributed macro is useful for loops, right? The loops that we have seen today. And especially for tasks that takes a similar time running, right? It's very useful. And the PMAP allows you to deal with a little bit more complex tasks that distributed, because here, even though the tasks don't take the same time, so PMAP can do a load balancing, right? So if it takes that some tasks already finished, then it can use the CPU resources to get another task and run that in an efficient manner. While if you use distributed, it will just wait, right, until the assigned iterations are available. Yeah. So this can do some workload. So here there is an example on how to use these functions. So here is a serial version that we have seen in the previous episode, yes, for computing the root square of the elements of some array, yes. And then if you want to use distributed, the first thing that we need to do is to make the function available on all the processes, right? And we do this with a decorator, yes. Otherwise, only the master process will see or will be aware of this function. So this macro here enables this function to be ported on all the processes available. So here is how to parallelize the function by using the distributed pmap and spawnat macros. And here we see how to create the workloads, right? We divide the entire length of the array by some value. This is the chunk size, right? And this will give us a batch piece, yes, a piece of work that can be used for the computation. So in the case of distributed, so essentially we take the for loop, but notice here that we are using the batch, yes, instead of the plain iterators as in the serial case. And then we decorate the for loop with a distributed macro. And this symbol here means that we want to collect, yes, the result, yes, in some particular array or variable. So this is me collecting, yes, and then we compute the summation that we define above. So pmap is here. So we take the pmap function, and this is using the function that we define for the batch or the chunk sizes, right? And this will be run over the batches that we created, yeah. And then finally, we can take the reduction operation here as a sum, yes? And this was done automatically with this symbol here in the distributed macro. So in pmap, we can take the sum explicitly with the sum operation and reduce the value that we get from pmap. So span-add requires more code refactoring, right? Because here we create a batch, but also you see that we need to partition the workload according to the workers that are available, and see that it involves a more partition, right? More refactoring, right? Then at this point, we create the futures, yes, that they are some instances that we place, but they are not executed instantaneously. So we create the futures that are stored in this array here. And finally, when we are or when we need the futures, then we can fetch them. And here I said that we can do other calculations while we wait for the results. So this is called asynchronous communication, because it allows you to overlap the work and communication, right? And this is useful for more complex tasks than simple loops. So we have seen how to use distributed and pmap macros, right? And there is a subtle difference in these two macros, right? And I mentioned that distributed is useful when the work is equally divided among all the workers. Yeah? So in the present case, it's very useful because the amount of work is almost the same. It's just computing the root square of the matrix element. But if the pieces of work are not evenly distributed, then a pmap is good, yes, or it should be better, because it is used, or it is it can be used as soon as some computing power is available. Yes, as I said, because if some task takes less time than the others, then once it is finished, yes, the worker can go and pick another task and do the job and continue in that way. So these macros can be used then for different types of problems. And in the case of span-add, you have seen that the code needs some refactoring, right? And but if the situation is more complex, then most likely span-add will be your friend there. So distributed can be used for reduction. We have seen the symbol plus, right? That will allow you to reduce some array or some operation. And it divides the range evenly for all the workers that are available. So pmap it starts with each worker, right? And as I said, some piece of job is assigned, And once it finishes, so the worker can go and pick another task, and it doesn't wait for the number of iterations that is assigned statically as in the distributed macro case, right? So that's why this allows you for more load balancing, and this is not a feature in distributed. So SpanAt deals with futures, right? This is a concept, and this is asynchronous, right? And can be used for uneven workloads. So if you run the examples, especially for the root square operation that I show you in these cases, right? You will see that you don't get a significant speed up. And that's why that's because the root square operation is highly efficient in languages like Julia, right? And it doesn't add anything useful if you parallelize this type of computation. To see some significant speed up, the function that is executed needs to be heavy enough or needs to be expensive. So this is one recommendation, and this is one trick. Yes, in the case you want to simulate the root square operation, so you can add some sleeping time, low sleeping time, so that you can mimic, yes, a more expensive operation. And then in this case, you can see a more significant speed up. But this is just a trick. Yeah? In more realistic situations, you don't need to parallelize the root square loop, let's say. So here there is an example for map and pmap, yeah, using the linear algebra package that we saw before. And here you can see that pmap can be used to parallelize some linear algebra operations, right? And this will use the available threads, yes, or the available workers, right, that are in the system. If you don't want to run the program in serial mode, then there is the function uh, map, yes, which will run in serial mode. So shared arrays. So I mentioned previously that in the distributed computing in Julia, there is also the possibility to do some shared memory programming. And this can be done with the shared arrays. And this will scale for the single node, right? So here we have an example for the square root of the elements of the matrix, right? We have seen that previously. And here we can use a shared array, yes. And this will allow us to update the values of the shared array A, right? And the threads or the workers, sorry, the workers will be able to write on the same memory address. So here we are using the decorator distributed for the for loop, but also we need to synchronize the workers at the end of the for loop. Yeah? And we use the sync decorator. So the advantage of the shared arrays is that the memory is already there, so you don't need to transfer the data, and that's why it can be more convenient to use that when you are on a single node, for instance. So here there are some references, and here there is an example of a shared array. here we start with the matrix or a random number matrix, right? And then we compute the square root of the elements of the array. But then we can also define a shared array, yes, a shared array, and then compute the function by using the shared array. But remember that this function is overloaded, yeah, because here we are using the definition for the shared array that was created here. So this function is shared array, but it's based on the array that is created here, shared array. And it contains the distributed decorator, while the other shared array is for a plain matrix. So then you can time the code. Let me see if I time that. Let me see. Learn distributed share. So here is the result in the case of the serial operation, right? I'm using some threads, four threads. Yes, you can see here the time that it takes. Yes, and here in this case, you can see the time. Okay. So notice that there are two macros for getting the timings. So this is the time macro, and this will do or this will collect the timing for a single evaluation. And so if you want to be more precise or to get a better statistics of the timings, then you should run several times this line to get a more reliable results. But also you can use the btime a macro, which is contained in the benchmark tools package, but you need to install or add it to your Julia installation, right? It's not shipped with the standard library, and then you can get a more reliable result. Also, how to compare, yes, the method that is being dispatched for A and SA. If you see here, the method looks the same, yes, except for the name of the variable looks the same, but actually they refer to two different methods, right? As it's here, yes. So this is allowed in Julia to have several definitions for several methods for the same function. So distributed arrays. So in this case, we have pieces of data on several processes. So this is in contrast to shared arrays where all the data is shared by all the processes, right? Or all the processes can see or are aware of that data. But in the case of distributed arrays, each worker has its own piece of data. And this can be useful if you have a very large arrays of data. Yeah. So in the case that data doesn't fit a single node, then you could get this option, yes, in Julia, and the data can be distributed across different nodes. Here there are some examples that you can run, yes, exercises, yes, for shared arrays, and also for the distributed computation of pi.